So the transport layer functions, layer 4 functions, are going to be covered by user datagram protocol, UDP, or TCP, transmission control protocol. Again, the transport layer and UDP and TCP are both going to be there for how we deliver this information from one of these entities to another, from one of these laptops or one of these voice over IP phones to another. So UDP is lightweight and quick, and therefore good for real-time applications like voice. TCP, on the other hand, is not as quick. It is more overhead, more header information, and basically provides the reliable delivery of data. So we use TCP for data, UDP for voice. The session layer simply keeps track of the upper layer application, and it's accessing the lower networking layers. So if, for example, you have a network, let's say you're running Skype and you're running Halo and you're checking your email all at the same time, the session layer function is basically going to help keep track of those so that you know that, hey, this bunch of zeros and ones belongs to Halo and these bunch of zeros and ones belong to your email and so on. So the session layer basically just helps keep track of that function. The presentation layer is simply how things are formatted, whether they be in ASCII format, MPEG, JPEG, or how are the zeros and ones formatted and how are they presented to the upper layer. The upper layer application is fairly simple. It's normally that which you and I would interface with a keyboard, mouse, camera, or some I/O input-output device, and the application again would bridge between humanoid and machine, or in this case a PC. Now, depending on where you are in this OSI model, when you refer to that clump of zeros and ones or that group of zeros and ones, the group or zeros and ones is referred to as something different. For example, if you're referring to the zeros and one grouping from the application to the session layer, it's simply referred to as a PDU, or protocol data unit. That's simply a generic term to express a group or a clump or a chunk of data. It's a grouping of zeros and ones. If you're referring to that group of zeros and ones down at the transport layer and you're using user datagram protocol, you're then in fact going to call that group or clump UDP datagrams. If you're using TCP, transmission control protocol, that grouping of zeros and ones is going to be referred to as a TCP segment. Down at the networking layer, layer 3, the grouping of zeros and ones is referred to as packets. The grouping of those zeros and ones at the layer 2 data link layer are referred to as frames. We say Ethernet frames, frame relay frames, HDLC frames. These are all example of layer 2 technologies. And at the physical layer, the data traffic, or the zeros and ones, literally are individual, a 0 or 1 or bits, the smallest element of data that can exist, a single bit. Now the way that this works is we have two of these laptops. Each one, remember, is going to have this OSI model function inside of each one of them. And we're going to take from the hard drive of the laptop on the left here a JPEG image of my dog Barker, our dog Barker, I should say. He's our baby, 90-pound sack of joy. And we're going to take that 3 megapixel photograph that exists on this hard drive, and we're going to transfer it over the Ethernet. We're connected via Ethernet at the bottom of the physical layer to the other PC's hard drive. We're going to be using file transfer protocol. FTP is going to be the application at the application layer. We're going to take some number of zeros and ones. Now we're limited to the Ethernet length. The Ethernet frame length, that grouping of zeros and ones down here, can only be 1500 bytes in regards to what it can carry. So we have to limit. We have a 3 megapixel, will not fit into 1500 bytes. So we have to take something less than 1500 bytes of the photograph on the file, and we're going to stuff that into a TCP envelope. And when I say stuff that, what I'm really saying is we're going to put a TCP header, which is just nothing more than another grouping of zeros and ones in the front part of the zeros and ones that make up the portion of that photograph. So we put a TCP header on it. We put on the TCP header something called a port number. There is a field, a 16-bit field inside the TCP header that allows you to indicate what port number you're using. Now, a port number for TCP or UDP is not a hole in the front of a router or switch. In fact, a port number is nothing more than an identifier of the application from where it came, so that when it gets to the other side over here, it can know the application to whence it's going to go, FTP. So we're going to use well-known port number 20, which identifies FTP as the application. We take the TCP header and we place it into an IP header or an IP payload, and we put an IP header on it so that we can route it across the World Wide Web. Inside the IP header is going to be an IP address 192.168.1.1, and now we can route this across the World Wide Web. We then in turn take the IP header containing the TCP header, which contains eventually the user data, which is the picture, and we're going to place that into an Ethernet envelope. Truth being told, we're going to place an Ethernet header on it, and that's going to have the hardware or the MAC address, media access control, of the device on the right hand side. We're going to send this Ethernet frame 1 bit at a time, 10 million bits per second, until it arrives on the other side. We're going to receive those bits 1 bit at a time, 10 million bits per second, until all the 1500 byte Ethernet has basically concatenated, and we have the Ethernet frame on the other side. Inside the Ethernet frame is a field in the Ethernet header called the type field. And if we examine the type field, it's going to tell us, hey, the contents of this Ethernet frame go up to IP. So we remove the Ethernet header and we send it to IP for processing. We then look at the IP header, and in the IP header is a very similar field that identifies TCP or UDP. In the case of TCP, the protocol type field would be 06, and that says, hey, this content of this IP payload goes to TCP. We strip off the IP header and send it to TCP for processing. We then examine the TCP header, and in it is going to be a port number. Port number will have a value of 20, and that receiving device says, hey, port number 20, I know that that's the well-known port address for file transfer protocol. Strip off the TCP header, send it to FTP for processing. FTP, file transfer protocol, the application will receive and concatenate all these little pieces over here until the equivalent of the file on the left has transmitted to the file on the right. TCP is responsible for the, quote, reliable delivery of these TCP segments. If one is corrupted or one doesn't arrive or it arrives out of order, it's TCP's job to make sure that it gets corrected. Same thing or similar in the voice over IP world. We have these zeros and ones that are going to be created from the voice over IP phone, perhaps. There's a codec in here. We're going to take the audio sound from someone's voice, we're going to run it through a coder decoder or a codec and generate a stream of zeros and ones representing the voice in a digital form. We take that grouping of zeros and ones, and in this case the application real-time transport protocol is going to take some number of zeros and ones and place them into a UDP header. The UDP header is going to have a port number that the two phones have to agree on beforehand in order to transmit voice over IP. It may be 53,000, whatever, just some random number. We then take that UDP header with the voice, this very small quantity of voice, and place it in an IP header for routing across the World Wide Web. We take the IP header and its contents and put that into an Ethernet envelope and then put the destination hardware address in there. We send that across until the Ethernet frame's built up. We examine the type field in the Ethernet header, strip off the Ethernet and send it to IP, examine the type field in the IP header, strip that off and send it to UDP. We look at the port number and say to ourselves, hey, that's the port number that I agreed to receive voice over IP on. So this in turn goes to the application RTP. RTP will basically feed that back through a codec, converting that from its digital form of zeros and ones back into the analog sound so that it can be heard. The only difference here is the reliability is not added there. We don't need the reliability. We're using voice over IP. We can lose some of these packets. It's not that big of a deal.